is scattering. Okay, three things are there: transmission, scattering, and absorption. Which one will be important for remote sensing of the Earth? Transmitted or scattered or absorbed? No, transmitted. The one which is transmitted means to pass through. It can pass through. Scattered, it will go in different directions. Okay, so you cannot use it for remote sensing. You will use only the transmitted rays, electromagnetic radiation, which are transmitted through the atmosphere and reach the surface. So, can all the electromagnetic radiation be transmitted through the atmosphere? Can all electromagnetic radiation pass through the Earth's atmosphere? No. What happened to some of them? Yeah, I mean they are absorbed, some may be scattered and some of them are absorbed. They cannot pass through the Earth's atmosphere. So, we have a thing called atmospheric window. What is the atmospheric window? Atmospheric window shows the parts of the electromagnetic radiation which can pass through the Earth's atmosphere. Okay? So, are X-rays a part of atmospheric window? X-rays?
No, it's not.
No, it is not a part of the atmospheric window. Why? Because it is absorbed in the Earth's atmosphere. Are gamma rays a part of the atmospheric window?
No.
No, gamma rays also are not a part of the atmospheric window. What about visible light?
Yeah.
Is it a part? Yes, it is a part of the atmospheric window. Similarly, parts of the infrared, most of the parts of infrared, they can pass through the Earth's atmosphere, so it is a part of the atmospheric window. Same is the case for microwaves and same is the case for radio waves. Okay? So they can pass through the Earth's atmosphere and reach the surface of the Earth. Now once the electromagnetic radiations reach the Earth's surface, what happens to them? Are they absorbed? Are they reflected? Are they transmitted? All the three can happen. All the three can happen. Part of the radiations, they may be absorbed by the surface of the Earth. Part of them may be transmitted. Transmitted especially if they are falling on water bodies like lakes or ocean. So some part of the light, it will pass through the water and then later on it is absorbed. And some part of the radiations are reflected. So which part will you use for remote sensing? The one which is absorbed, the one which is transmitted, or the one which is reflected? Reflected or transmitted? Transmitted you will use when it is coming from the atmosphere. When it reaches the Earth, you will use the reflected one. Okay? The radiation which is transmitted through the Earth's atmosphere, it will reach the Earth's surface. Now, from the Earth's surface, it has to be reflected back, then only your sensor will detect that reflected radiation. Now, I told you that if you see the images in one particular wavelength, okay, say wavelength for blue or wavelength for green or wavelength for red, in one wavelength, what will be the color of the image?
What?
If you observe, if you see the image of an object in one wavelength, what will be the, or one band, what will be the color? Gray scale. It will be in gray scale, black and white. Means to see the color image, how many bands you need? Three bands, red, green and blue. Then only you will see the object in a colored format. Otherwise, if you are observing in one band, it will be in gray scale or black and white. Now, if the absorption is strong, if the rays are electromagnetic radiations are absorbed by a particular object on the surface of the Earth, what color will it appear? No, everything is absorbed, nothing is reflected. What is the color of this mouse? Black. If it is absorbed, color of your hair or color of your jacket, soap you are wearing, all the radiations are absorbed. So if it is absorbed, then it will be black. Okay. and if it is reflected,
White.
then it will be white. In gray, it means if you are observing the image in gray scale, in black and white, then if the reflection is low, then the object will be dark. If the reflection is more high, then the reflection will be white, close to white, or the object will appear bright in color. Now, if you see the color image, depending on the radiation which is reflected strongly, you will see the color of that object, the object in that particular color. For example, that chair is appearing orange in color. Why? Because all the other radiations, they are not as strongly reflected as the orange one. Orange one is reflecting more. So you are seeing the chair in orange color. Similarly, I was telling you about vegetation. That vegetation, the leaves or the plants or the crops, forests, they appear green in color when you see in natural light, natural color. Why? Because green color is reflected more than red or blue, so it appears green in color. Now, we said that our eyes, we cannot see beyond the visible part of the electromagnetic radiation. We cannot see infrared, we cannot see ultraviolet, we cannot see microwaves or radio waves. But scientists can design sensors which can detect those radiations which are invisible to our eyes, which we cannot see. So, means there are radiations present around us, but we cannot see because they are beyond, they are outside the visible region.
Like X-ray?
Like X-ray, but X-ray is not present around us. Why? We don't have X-ray over here, or if you go out, you don't have any X-ray.
Because it's much faster.
No, it is absorbed by the, so you don't have X-rays, means from the sun, the X-rays cannot reach the surface of the earth because they are absorbed. Yeah, if you have an artificial source, then yes, it will be there. Like in the hospital, you have X-rays. The X-ray is there, but you cannot see it because it is invisible. It is beyond the visible part. Only between the violet and the red portion, between 0.4 micrometers to 0.7 micrometers, we can see. Now, I was telling in the last class that some of the objects on the Earth's surface, they reflect more light, more radiation in parts of the electromagnetic radiation which we cannot see. For example, vegetation, leaves, they reflect more infrared as compared to red or green or blue. But can we see the infrared? No, we cannot see the infrared, so we have no idea about the reflection. But if you see that vegetation in infrared, if you have an infrared image, and I told you in one band the image will be in grayscale. So if you look at the infrared image of the vegetation will, since it is reflecting more infrared, it will appear very bright in color because the reflection is more. Okay, so you have, can you see this?
Yes.
What is the color you see?
No.
Green is there and this is black. So this is a natural color image. This is how, what is green and what is black? Again.
Grass and tree
Green means it is vegetation, forest. Trees, yes, forest it is. This one is a forest and this one is a valley. It's a river, maybe flowing water. Yes.
Looks like mountain.
Now, look, yes, you are right. The image is from Amazon. Okay, good observation. So, this one is a natural color image. Okay, now I will separate it into different bands. Okay, now you have one image, this image for the same area in blue band, this one is in the green band, this one is in red band, and the other, this one is in the infrared. Now, where you see the brightest image? In blue or green or red or infrared? Bright, white. Infrared is the okay, so infrared which you see is bright. And why do you see the vegetation very bright in infrared?
Because the whole color reflected
Okay?
The red one?
No, see, if something is not reflected, you just simple principle. If the reflection is high, the object will be bright.
No.
Bright. If the reflection is low, the object will be dark. Okay? So, more reflection, brighter, or if it is grayscale image, it will be white in color. If low reflection, then it will be darker in color. Okay, is there any reflection in this from the blue band for vegetation?
No.
Not
Do you
very
see
high.
black, or there is
Mid reflection.
not very strong reflection is there? Otherwise, if the reflection was not there, it will appear black. There is some reflection, but it is less as compared to green. Okay, it is more than red, but less than green and much less than infrared. So maximum reflection, where do you see? It is in the infrared. Infrared is reflecting the most. So that means if you see the image of, if you see an infrared image of vegetation, it will appear very bright in color because it is reflecting most of the infrared radiation. But since we are not seeing, if I remove, okay, forget about the infrared now. See blue, green and red. Which color is reflecting more? Blue or green or red? Green is reflecting more. So, because you are seeing in a single band, it is appearing as white. But if I combine the red, green and blue, what will be the color of vegetation? Green, because green is reflecting more. If I combine the three images together, like it is here, the three images are combined. This one here, the vegetation is appearing green because green is reflecting more. Now I separated it into 3 or 4 different bands. Okay, so green is reflecting more as compared to blue and red, but it is more reflecting most in the infrared region. So the reflectance or the means reflection for different wavelengths for a particular object changes. It is not the same for some region. For it will be low, for some region it will be high, for some reason, for some regions of the electromagnetic radiation there will be no reflection at all. Now look at water in this case. This is the river which is flowing through the forest. Now you see there is some reflection of water in the blue, in the red, also there is some reflection in the green region. Of course, it is more brighter in blue. What is the color of water normally?
Blue.
Blue color.
Blue.
Okay, so if you see this one, the reflection means it is slightly brighter than red and green. Okay, so water appears blue. But look at infrared. What is happening to water?
So dark.
It is dark. So that means what is happening?
Absorbed.
It is absorbed. All the radiations are absorbed.
And then
Means the water means all the means there is no infrared radiation reflected from water bodies. All the infrared radiations, they are absorbed. So if you look at, if you have to find the contrast between water and river, which one do you think is the best one to look at? No, contrast means difference, big difference between reflection. Infrared will be the best because vegetation is reflecting the maximum and water is reflecting the minimum. It is absorbed, so the difference is huge. So this thing you have to keep in mind for remote sensing. In remote sensing, this is an example for water and vegetation. To identify any, for example, you have to identify a rock. You have to separate an igneous rock from a sedimentary rock. Okay. Now you have to check for different bands and the place where you see the maximum difference in the reflection, that will be the best band to identify. If the, like for example, if you look at vegetation and water in blue band, okay, there is some contrast, but the contrast is not very high. The reflection is almost the same, not very big difference is there in the blue region. But if you look at in the infrared region, there is a big difference in the reflection. So it's better to observe water and vegetation in infrared. Yes.
But how do you know it's not an igneous rock, not an sedimentary?
First you have to separate between the two. Means you have to make sure that this rock type is different from this rock type. Okay. then okay, you have the geological maps of the area, you can cross check with that what is this rock type on my remote sensing image which is appearing dark in color. You correlate with the geology map, you use GIS, superimpose and see if it gives you the answer, it is fine. Okay, you know your answer. Or sometimes if it is a new area, you may visit that area also. One location you can visit instead of visiting the whole area. You can visit one area and just check what is the kind of rock, and then you
After that,
you match with
remote
your,
sensing.
yes, exactly.
Thank
So
you.
this is how it is done. So going back to the slide. Every time I have to start from the beginning. Okay, so talking about the radiation target interaction. What do you mean by target? Target is any object or any part of the Earth's surface which you are interested in observing through remote sensing. For example, you are interested in observing the rock types which are exposed. So the rocks become your target. The target, a person who is working in the field of agriculture, he must be interested in observing the fields, agricultural farms. So the farms become his target of interest. Someone is working in field of water. So the water bodies or rivers become the target of interest for him. So the target is anything which you are interested in observing on the remote sensing image. Okay. Now, how does the electromagnetic radiation interacts with the target? When the remote sensing, the radiations fall on the Earth's surface, we saw that either some part of the radiation will be absorbed, some part will be transmitted, and some part will be reflected. So, we will be interested in the part which is reflected from the target into the atmosphere, where the sensors record that reflected energy. And the thing which you have to remember, if reflection is more, the object will be bright or white in color. If the reflection is less, the object will be dark in color. Okay. Now, the reflection which takes place from the Earth's surface, there can be two types of reflection. That reflection, one is called as specular reflection and the other one is called as the diffuse reflection. Now, what is the difference between specular reflection and diffuse reflection? This is an example of specular reflection. This is an example of diffuse reflection. Do you see any difference between the two?
Yes.
What is in the specular reflection?
Specular, the sign when you send it,
Yeah.
it's
All the direction, all the radiations are reflected in the same direction. And what about the
area
surface? Surface is smooth, it is plain, smooth surfaces. So, specular reflection normally takes place from smooth surfaces, whereas diffuse reflection, it takes place from rough surfaces, okay? Not smooth, it is rough, uneven surface, okay? Mountains, of course, will be included in that. And the reflected radiations, okay, they are reflected, but they are not all radiations are not in the same direction. They are in different directions. But of course, they are reflected back, and they can be recorded by the sensors. Now, the reflection which is taking place from the Earth's surface, from different objects on the Earth's surface, they are normally a combination of diffuse and specular. Most Earth's features lie somewhere between perfectly specular or perfectly diffuse. Diffuse reflection will be from irregular, uneven surfaces, and specular reflection will be from even surfaces. Can you give me an example of an even surface? From where? A smooth surface from which? Yes?
like the sea.
Like the sea, exactly. The water in the sea, it is like smooth, and you will have specular reflection. Okay? Now, we have an example here of specular and diffuse reflection from leaves. The same thing which I was telling you before. Here in the bottom you can see you have the three types of leaves. One leaf is healthy and the other one is dead or it is unhealthy leaf. Now the arrow is indicating the amount of different electromagnetic radiations which are reflected from the leaves. The length of the arrow is indicating the amount of reflection. Bigger the arrow, more the reflection, smaller the arrow, less is the reflection. So if this one is a healthy leaf, okay, and you have the 4 radiations which are given here, red, green, blue and near infrared. Near infrared in short we write as NIR, near infrared. So where is the maximum reflection taking place for the leaves, healthy leaves? In the near infrared, because if you look at the arrow is longest for the near infrared, which indicates the maximum reflection for leaves occur in the near infrared region. But can we see the near infrared with our eyes? No. But okay, if you remove this near infrared, then where is the maximum reflection taking place? In green. And what is the color of leaves normally you see? Green. This is the reason. Why? Because more reflection is taking place from the green leaf. Now if the leaf is dead, or if it is unhealthy, or if it is under some kind of stress, what happens? The amount of near infrared reflection which is taking place, it reduces, it will be very low. Okay? So using near infrared radiations, you can easily differentiate between healthy and unhealthy leaves. If the vegetation or the crops, they are healthy, they will reflect strongly the near infrared radiations. If they are dead, or they are unhealthy, or if they are under some kind of stress, the amount of reflection from the near infrared will reduce. So using this understanding of reflection of the near infrared from healthy and unhealthy vegetation, it is very easy to find whether the plants are healthy or unhealthy. Okay? Then again, you come to the specular and diffuse reflection in water. So what is the color of the water normally you see? Blue in color. Means if water is present in large quantities, it appears normally blue. Sometimes it can be greenish blue or dark blue, light blue, different shades of blue may be there. Now in the visible region it is appearing blue, but what happens is if you go into the near infrared region, it is just the opposite of vegetation. Water absorbs all the near infrared rays. So in the near infrared region there is no reflection from water, and if you observe a water body in near infrared radiation, it will appear completely dark, it will appear black in color. So you can easily differentiate between water and vegetation using the near infrared radiation. Okay? So you can see here. Now this slide I don't think so you have with you, but the one which is given, it is the same thing. It's not different. Just it's a bigger slide, so I added it here. So this line which you see here, okay, this is showing the amount of reflection, percentage of reflection which is taking place for different wavelengths. Okay. So what are the different wavelengths here? Here you have the visible part of the electromagnetic radiation. Blue, green, red, and then you have the near infrared and the far infrared and so on. And what is this line indicating? It is showing the percentage of reflection. If the line is high, means it is showing more reflection. If it is below, then it is showing more absorption or low reflection. Now this green line, if you see, this is for vegetation. Where do you see the maximum reflection for vegetation? In which part of the maximum reflection, where do you see?
Reflection?
Yes. In the near infrared, you see the maximum reflection for the vegetation. Okay. And what about water? Do you see any reflection for water in the near infrared? No. If you see, this is the spectral reflectance curve for water. Okay. It is there, some reflection is there in blue, green and red, but as it reaches the infrared, what happens? It goes down, there is zero reflection. Okay? So, it will be in dark color, vegetation will be like very bright, and water will be very dark. So, this is just an example for water and vegetation. And this curve which you see, this is called as a spectral reflectance curve. What does it show? It shows the amount of reflection which is taking place for different wavelengths of the electromagnetic radiation. On the x-axis, you have the wavelength of the electromagnetic radiation. On the y-axis, you have the percentage of reflectance. So if the reflectance is high, the curve will be, it will go higher. If the reflectance is low, the curve will go down. Okay? So by measuring the energy that is reflected by targets on the Earth's surface over a variety of different wavelengths, we can build up a spectral response for the object. What I showed you here, this is a spectral reflectance curve for different objects. How many objects are shown here? 3. This is the curve or spectral reflectance response for 3 objects: dry soil, vegetation and water, which is given over here. Now, by comparing the response pattern of different features, we may be able to distinguish between them where we might not be able to if we compare them only at one wavelength. So, instead of looking at these things, different things at one wavelength, you have to see them at different wavelengths. You have to see the reflection in different bands. Where you see more reflection, then only, okay, if you have to find out the difference between bare soil and vegetation, which part of the wavelengths you will look for? Near infrared or far infrared?
Far infrared.
In the far infrared, if you see, there is
12.9.
maximum difference. Okay, the reflection, there should be maximum difference in the reflectance of 2 objects to easily identify that. If you, for example, if you look in near infrared or far, means the longer part of the near infrared, you will see that soil and vegetation, they are
The same.
almost same. So it may be difficult for you to identify. So that is why it is written that to differentiate or to identify your target, you have to look for it in different wavelengths, in different bands, and wherever you see the maximum difference, that band will be used for identifying. Okay? Now here is an example of, again, water and vegetation in natural color, and next image I will show you in near infrared. So vegetation is appearing green here. Also water you can see clearly because it is carrying sediments. So because of that, the color of water is slightly yellowish. Now if I look at the same image in the near infrared band, what will be the color of this water
Dark.
and what will be the color of vegetation?
Dark green.
Yes.
I think there will be no contrast.
No contrast?
Yes.
I am talking about near infrared. You said the water will be black. Okay, I agree with that. Water will appear black. And what about
dark
with-
green?
Maybe
No.
Will be
Near.
white.
I am all talking about one band. I am talking about near
Yeah,
infrared.
it will be white.
Oh, will be white.
White. Okay, so vegetation will appear white in color because in near infrared, maximum amount of radiation is reflected from the vegetation, and water absorbs all the near infrared. So water will appear black and vegetation will appear white. This is the same image, but this is in infrared. This is infrared image. This is band 5. This is an image from Sentinel. Okay, Sentinel is a satellite, land observation satellite, which belongs to the European Space Agency. You have heard the name of Landsat. Landsat belongs to United States, USGS, NASA and USGS combined. This one is from the European Space Agency. Now, for different images, the band combination or the band designation is different. For example, for Landsat, infrared is band 4. For Landsat imagery, band 4 corresponds to infrared. For Sentinel imagery, band 5 corresponds to infrared. Okay, forget about that, we will see that later. But right now, what is important here to see how you can easily differentiate between 2 objects by looking at it in a particular wavelength or in a particular band. So here in the natural color, water is showing as yellow, and then you have the vegetation which is appearing in green. When we use the same image in the near infrared band, or sorry, in the infrared band, you see all the vegetation, it is light in color or bright in color, and all the water bodies, they appear black. So it gets very easy to differentiate between water and vegetation if you observe them in the infrared region, near infrared region. Okay. The same thing is shown here, the spectral reflectance curve which I showed earlier for water, vegetation and soil, how they reflect in different parts of the electromagnetic spectrum. So water, again you will see that as you move to the near infrared region, all the water is absorbed, but the vegetation, it reflects most of the infrared, so it becomes easy to differentiate between them. Then coming to passive versus active remote sensing, you have already some idea about this. What is the image on the left? What is it showing? Is it showing active remote sensing or passive? This one is passive. Why? Because you have a sensor here, and this sensor, it does not have its own source of electromagnetic radiation. It is depending on the electromagnetic radiation coming from the sun. So this kind of remote sensing is called as passive remote sensing. Whereas on the right side, you will see you have a sensor, and this sensor has its own source of electromagnetic radiation. It sends the electromagnetic radiation down to the ground surface, and then it is reflected back and it is recorded by this sensor. So this is active remote sensing. Active remote sensing is possible to do at night. True or false? Active remote sensing is possible to do at night. True. Yes, you can do, because it is not depending on the sun. It has its own source. So it can do at night, it can do during the daytime, no issue. But passive remote sensing, it cannot be done at night. It will, because it depends on the sun, so it has to be done during the daytime. So again, the same diagram explained slightly in a different way, just for your understanding. Okay. So in passive remote sensing, the sun provides a very convenient source of energy for remote sensing. The sun's energy is either reflected, as it is for the visible wavelength, or sometimes it is absorbed and re-emitted, as in the case for the far infrared or the thermal infrared wavelength, which is like emitted from the surface of the earth. And you have sensors which can record these reflected or emitted electromagnetic radiations, and then you can see them on the image. Okay? Remote sensing system which measure energy that is naturally available, they are called as passive sensors. They naturally available means the energy which is from the sun, that energy these sensors are recording. So this kind of remote sensing is passive remote sensing. And the important thing, they can be used to detect energy when the natural occurring energy is available. That means, I told you, when the sun is not there, or if it is cloudy, clouds are there, then you may not be able to do the remote sensing. For all reflected energy, this can only take place during the time when the sun is illuminating the earth. There is no reflected energy available from the sun at night. So therefore, passive remote sensing cannot be done at night. However, there can be the thermal remote sensing can be done at night also. What happens that as the sunlight falls on the surface of the earth, the earth's surface, it absorbs that energy, and during the night time when the sun is not there, that absorbed energy that is re-emitted. It goes out from the surface of the earth in the form of long wave infrared radiation, which we also call as thermal infrared radiation. So these thermal infrared radiation, they can be detected by the sensors even at night time, and they basically give you about an idea about the surface temperature of the earth. If it is like if you are talking in one band, say the thermal infrared band, then if the object is hot, it will appear bright in color, because it is reflecting more of the thermal infrared. and if the object is cool or if it is low, means it's not very hot, then the reflection will be low and it will appear dark in color in the thermal image. So this way you can detect the, get an idea about the surface temperature of the Earth. Then in active remote sensing, on the other hand, the sensors, they have their own source of electromagnetic radiation. They provide their own energy source for illumination. The sensor emits radiation which is directed towards the target to be investigated. The radiation reflected from that target is detected and is measured by the sensor. Now, of all the different electromagnetic radiations which are a part of the atmospheric window, microwaves are present in very small. Microwaves are a part of the atmospheric window, but the problem is that passive remote sensing from microwave is not possible. Why? Because the sun, it does not contain large amount of microwave. The amount of microwave which is coming from the sun, the microwave radiation coming from the sun, is very small in amount. So it is not possible for the sensors to detect that reflected microwaves. So because of that, most of the active sensors, most of the remote sensing which is done using active sensor, they use microwave. They have their own source of microwave. The sun does not contain sufficient microwave, but a source of microwaves can be created, and active sensors use this source of microwave. They send it down to the ground surface, and then the microwaves are reflected and then they are recorded by the sensor. So when we talk about active remote sensing, most of the time we are talking about microwave remote sensing. Okay. So similarly, okay, if microwaves, they are not present in the sun, we can use an artificial source of microwave, and you can do active remote sensing using microwaves. So same can be done with X-rays and gamma rays also. So why don't we do? Huh? Because of the atmosphere. Yes, you are right, because of the atmosphere. To be more precise, microwave is a part of the atmospheric window. What does that mean? It can pass through the Earth's atmosphere. It will not be absorbed. The only problem is that the sun does not have sufficient microwave to do remote sensing. Okay? So therefore, the sensors are designed which have their own source of microwave. It will pass, and where are the sensors? They are in the sky, they are in the atmosphere. So the sensor will, the micro, or in the space, the microwave will pass through the atmosphere and it will be reflected back and recorded. But on the other hand, you can do that same for the X-ray also. You can have a source of X-ray in the atmosphere and you send it down from the atmosphere to the ground and then record it. But yes, you cannot do it because X-rays, as soon as they pass through the atmosphere, they are absorbed. They cannot pass through the atmosphere. You have to remember about the atmospheric window. X-rays and gamma rays, they are not a part of the atmospheric window. That means they cannot pass through the Earth's atmosphere. Even if you have an artificial source, then also it will not, because the source is in the atmosphere or in the space. So the X-ray, it cannot pass through the space, through the atmosphere, it will be absorbed. So that is the reason why X-rays and gamma rays, you cannot use it for remote sensing in any way, remote sensing of the atmosphere, because they are absorbed in the Earth's atmosphere. Whereas microwaves you can definitely use, because microwaves, they are a part of the atmospheric window. Only thing is that the sun does not have sufficient microwaves, so you use active sensors which have their own source of microwave. So thing to remember here, when we talk about active remote sensing, we are mostly talking about microwave remote sensing. Active remote sensing means microwave remote sensing. Do we have time or it's done?
We just have 1 minute.
1 minute, okay.
One take, no.
I will take more, of course. So you have an image, difference between image and photograph. What is a photograph and what is an image? To just quickly, any image which is taken in the visible region, that means starting from 0.4 micrometers to 0.7 micrometers, that will be called as a photograph. Means the thing which you click with your mobile or a camera, that is a photograph, because that is taken within the visible region, which is from 0.4 micrometers to 0.7 micrometers. Anything which is taken beyond that, any image which is acquired in infrared, near infrared, far infrared, thermal infrared, microwave, or even in the ultraviolet, that will not be included in the photograph, that will be called as an image. So a photograph can be called as an image, no problem. A photograph, because it is in the any region of the electromagnetic spectrum. If you acquire an image, it will be called as an image. And a photograph can be called as an image, but an image cannot be called as a photograph, because the moment we use the word photograph, we are talking about electromagnetic radiations within the range of 0.4 to 0.7. In some cases, it's between 0.3 to 0.9 micrometers. Anything beyond that will not be a part of the photograph. So, and a photograph can be called as an image, but an image you cannot call as a photograph. You cannot say infrared photograph. No, infrared will always be an image. Okay. So this is the basic difference. So, okay, we will stop here and we will just continue with this in the next class. 2-3 slides are there, and then we will move to the next. Most of you are there for geological survey class, isn't it? 384.
Yes.
Tomorrow there is an important meeting. I don't know if you know about that or not. In the Bahu, in Hamad Al Jasir Hall, there is a meeting for our KSU or something like that, and most of us are going there.
So we will not have it.
We will not have the class tomorrow.
Okay.
I will send an email also, because some of you may not be there, so I will inform you. Meeting actually is from 1 to 2:30, and our class is from 1 to 2. So tomorrow means, and this course is not very big, geological survey, which we have a lot of time, we can finish.
نغير.